Let's try to understand transpose. So what is the transpose of a matrix? Let's say we have a matrix A with elements 1, 2, 3, 4, 5, and 6. So the order of this matrix is 2 rows and 3 columns, so it's 2 by 3. The transpose of this matrix will look something like this. So it will have, so what basically we have to do is that mm, we have to interchange the rows and the columns. So this row will now be our column 1, 2, and 3, and this row will be our second column 4, 5, and 6. So the order will be reversed. It will be 3 by 2. That's all about transpose. So now let's try to discuss some properties of transpose. Properties. So property number 1. So if we apply transpose on a matrix and we again apply the transpose, so it will be the original matrix back. Another property is if we add two matrices and apply the transpose, and so what we can do instead of this is we can apply transpose on individual matrices and then add them. In this case, we're first adding and then applying transpose, but here we are first transposing and then adding. So, the third property is applying transpose on A into B. So instead of this, we can also write B transpose first and then A transpose. So this is, and we know as in matrix multiplication, this is not equal to A transpose B transpose. This one is an important property. And in this case, it doesn't matter. We know the addition of matrices is commutative. We can write it B transpose, A transpose as well. So it doesn't really matter. So the fourth property is CA transpose, where C is a scalar. And what in this case we can do is we can take the scalar out. We can write C and apply transpose on A, and then apply the scalar later. So it's one and the same thing, whether we do it before applying transpose or multiplying it after applying transpose. So now let's talk about dot product of two vectors. So what is the dot product of two vectors A dot B? So it's equal to A transpose dot A transpose times B. So let's try to visualize this. If we have two vectors, let's say A vector and B vector. So A vector has an x component of A1 and y component of A2, where B vector has x component of B1 and y component of B2. So the dot product here is, first of all, we have to take the transpose of A vector. So it will be A1 and A2 and B vector as it is, so B1 and B2. So after doing these multiplications, and we can see we will get A1B1 plus A2B2. So that's the dot product. Well, dot product is also written as like this, A dot B with these pointing brackets. These are the two notations of dot product. So geometrically, A dot B, A vector dot B vector is the length of A vector times the length of B vector and times the cosine of angle between A vector and B vector. So we can write A vector dot B as length of A vector, which is this, and length of B vector, which is this. We don't have to write A1. So times the cosine cos and angle between them, which is, let's say, theta is the angle between them. So we can write this. So this is same as we have seen already, A1 B1 plus A2 B2. Now this we can see that if, let's say, we have B vector here and A vector here, we can see that this portion, that A length times cos theta is if we just see this, A times cos theta is this, the projection of the A on B. This dot product of A dot B is the projection of A vector in the direction of B vector. So as we can see, it's A cos theta times B, where these are the lengths A and B are the length of A vector and B vector. So we can also write it as projection of A in direction of B times B. So A vector dot B vector is also equal to this. So this is read as projection of A on B. Types of matrices. So let's talk about the types of matrices. The first type is what are row matrices and column matrices. So first of all, a row matrix is a matrix which has only one row. For example, we will have only one row, and here you can say we have three columns but one row. So it is 1 cross 3. So it is a row matrix. On the other side, column matrix have only one column and can have many rows, but have only one column. It can have many rows. So it is let's take 3 rows and one column. So it is 3 by 1. So now let's talk about what is a square matrix. We have already talked about this. Square matrix is a matrix which has same number of rows and columns. So when we have same number of rows and columns, for example, we have 3 columns and 3 rows. Here the order m cross m, the number of rows and number of columns are same. Okay, so that's square matrix. Now let's see what is symmetric matrix. This is another type of a matrix. Symmetric matrix. A symmetric matrix is a matrix when a matrix is equal to its transpose. And symmetric matrices are always a square matrix. So here A is a square matrix. And let's take an example. For example, we have a matrix, let's say 1, 2, 3, 2, and let's say 4, and let's say 5. 5 will be written here, 3 here, and let's say 7. Let's take the transpose of this matrix and let's see if it is equal to its own transpose. First of all, let's take a transpose and we can see for transpose we have to take this row and make it a column here, 1, 2, and 3. Take this row, make it a column, 2, 3, 2, 4, and 5. Take this row and it will be 3, 5, and 7. So we can see they are exactly the same. Here is 1, 1, 2, 2, 3, 3. So all the elements are again same. So we can say A is equal to A transpose. So this is a symmetric matrix. So, there is another type which is called skew symmetric matrix. Skew symmetric matrix. So, what is a skew symmetric matrix? It is also it is when A transpose is equal to minus A, or we can say a transpose is equal to its a square matrix is equal to its transpose but minus times its negative times the transpose of A. So here A is also always a square matrix. So let's take an example. We have a matrix A. Let's take the same example as we have already seen above. So let's take this example and see. First of all, let me erase this portion. Okay, so we can see this matrix, but this is a this is a symmetric matrix. We can just put negative here or negative just here, or let's say a negative here. And let's try to not transpose it. When we transpose this matrix, let's see what we will get is we have to transpose the first row, make it a column here, transpose this, make it a column here, minus 2, 4, and 5, and take this, make the column here 3, 5, and 7. One thing I forgot to mention that for a matrix to be skew symmetric matrix, the diagonals must be 0. We cannot have any the diagonals. The diagonals must be 0. Now we will have 0, 0, 0 here as well. So now let's see if they are equal but of opposite sign. Now if you multiply negative here, we will see A minus is 0, minus 2, positive 3, positive 2, 0, positive 5, positive negative 3, negative 5, and 0. So we can, yeah, maybe we have done a mistake here. Yeah, we have transpose taken this here, we have taken this here, so it is a negative here, sure. So we have a negative here as well. So we can see both these are exactly the same. This is same as this. So A transpose equal to minus A. So that's the skew symmetric matrix. So the property of the skew symmetric matrix is, remember that the diagonal elements are always zero. Now let's talk about diagonal matrices. So what is a diagonal matrix? This is the fifth type of matrix. It is a diagonal matrix. So what is a diagonal matrix? So a diagonal matrix is a matrix if all elements on diagonal elements are non-zero and the remaining elements are zero. For example, we have a diagonal element if we have element if let's say we have a 3 by 3 square matrix and the diagonal elements are must not be zero. For example, this is a diagonal matrix. Here let's say it's a matrix. Here Aij, which is a general term of an element, is equal to zero if I is not equal to j. So that means when I is not equal to j, here this is the first row, this is the first row and the first column, this is the first row and the first column, this is the second column, third and third column. So for all other elements where I is not equal to j, these elements are zero. Also have something called as rectangular diagonal elements. So square matrix, but a rectangular diagonal matrix is a matrix which is not necessarily a square matrix. For example, we have 1, 0, and 2. We have 2 rows and 3 columns. So here the diagonal is this. So it's not a square matrix. The order of this matrix is 2 by 3. So this is called a rectangular diagonal matrix. Now let's move on and see if we have a sixth type of a matrix, and it's called identity matrix. So an identity matrix is a matrix where all the diagonal elements are 1 and all the non-diagonal elements are 0. I mean, all the diagonal elements are 1 if I equal to j, and it will be 0 if I is not equal to j. Also, in case of identity matrices, these matrices are always square matrices. So let's take an example. A is identity if all the diagonal elements are 1, where I and j are equal, as you've seen here. Here I is 1, j is 1, here I is 2, j is 2, so on. And other elements are 0, where the I and j are not equal. So now, the property of an identity matrix is that if we multiply an identity matrix with any other matrix, we will get other matrix as it is. So now let's see another type of a matrix, which is called a scalar matrix. So what is a scalar matrix? A scalar matrix, first of all, they're also always a square matrix. And in case of scalar matrix, the diagonal elements are a scalar quantity. For example, instead of 1, we have, let's say, a lambda, a scalar quantity. Okay, so this is a scalar matrix where Aij equal to lambda if I is equal to j and 0 otherwise. So actually, an identity matrix is also a special case of scalar matrix where lambda is equal to 1. So let's move on swiftly and see we have the eighth type of a matrix called zero matrix. So what is a zero matrix? Or we can also say a null matrix. So a matrix when all the elements are zero. All elements are zero. For example, let's take a square matrix of 3 by 3 where all the elements are zero. So this is a zero matrix. And if we multiply any matrix with a zero matrix, we will get back a zero matrix. So another type of a matrix, we have an triangular matrix. So we have two types of triangular matrices, and the first one is upper triangular matrix. So an upper triangular matrix is a matrix if all the elements which are not in the upper triangular part are zero. I mean, let's take an example. Let's take a 3 by 3 matrix. All the elements which are not in the upper triangular part are zero. That means these elements will be zero, and these elements are not zero. So all the elements which are not the part of the upper triangular are zero. So these are zero. Then this matrix is said to be an upper triangular matrix. So we also have another matrix called lower triangular matrix. So when we have the non-zero elements on the lower side, for example, let's take 1, 2, 3, 4, 5, and 6. If all the elements which are not in the lower triangular part of the matrix, when they are zero, it is said to be a lower triangular matrix. That means these elements will be zero. So this is also a 3 by 3 matrix. So all the so you can see we have a diagonal here, and all the elements which are above the diagonal are zero. Only the elements in the lower in this area, in this portion, and the diagonal elements are non-zero. So it's called a lower triangular matrix. So that's it. We have seen the 10 different types of matrices. Let me recall. And the first one was we have seen the row and the column matrix, and then square matrix where the order is same, where the number of rows is equal to number of columns. Symmetric matrices where a matrix is equal to its own transpose, and skew symmetric matrix is where a matrix is equal to its negative times its transpose. And the important thing is that here all the diagonal elements are zero. Then we have a diagonal matrix where all the non-diagonal elements are zero and all the diagonal elements are non-zero. And then we have seen a rectangular diagonal matrices where the number of rows is not equal to number of column, and all the these elements where I is not equal to j are zero. Then we have seen an identity matrix where all the diagonal elements are 1 and all the non-diagonal elements are 0. Scalar matrices where diagonal elements are equal to some scalar value. It can be anything like 2, 3, it can be anything. So 0 matrix where all the elements are equal to 0. Upper triangular matrices where upper all the upper matrices which are above the diagonal are non-zero, including the diagonal. That means all the all the elements which are lower the diagonal below the diagonal are 0. And in case of the lower triangular matrices, all the elements which are above the diagonal are 0. So only these value are non-zero, which are in the diagonal, and the elements below the diagonal. So yeah, that's it. In the next video, we will talk about determinant of a matrix. Okay, see you then.